Hi there, I'm Colin, and I'll be your narrator for today. In this module, we're going to learn how to differentiate composite functions using something called the chain rule. In day 1, we revised the notion of a composite function, sometimes called a function of a function. For instance, consider the function y equals the square root of x squared plus 3. Observe that x squared plus 3, a function in its own right, is nested within the function that square roots everything. Therefore, x squared plus 3 is the inside function of the composite function, and the square root function is the outside function. If we are able to explicitly identify the inside and outside functions, like we did above, we can use something called the chain rule to differentiate the composite function. Specifically, if we call the inside function u, then we can write y in terms of u. The chain rule then states that our derivative dy dx is equal to dy du times du dx. That is, dy dx is simply the product of two simpler derivatives. Note that the chain rule is sometimes expressed in what is called functional notation. Although this form looks very different to the one above, they're exactly the same. If all of this notation is bugging you, perhaps describing the mechanics of the chain rule in a single coherent sentence might help. Specifically, the rule states that if f is the outside function of the composite function, and g is the inside function, then the derivative of the composite function is equal to the derivative of its outer function, with its inner function thrown in as input, multiplied by the derivative of the inner function itself. Alright, let's now use the chain rule to differentiate the composite function y equals 2x minus 1, all raised to the power of 7. We first identify the inner function u as the function 2x minus 1. This means we can now write y in terms of u, namely y equals u to the power of 7. The chain rule then states that our derivative dy dx is equal to dy du times du dx. So now all we have to do is calculate these two smaller derivatives and multiply them together. Since y equals u to the power of 7, dy du is equal to 7 times u to the power of 6, using the power law for differentiation. And since u equals 2x minus 1, du dx is just 2. Our answer must be in terms of x, so switching u back to 2x minus 1, we thus have our derivative dy dx to be the following. Let's look at another example. Consider the composite function y equals x squared plus 3, or square rooted. We first identify the inner function as x squared plus 3, as we did earlier. This then means we can write y as the square root of u. The chain rule then states that the derivative dy dx is equal to dy du times du dx. Since y equals u to the half, dy du is a half times u to the power of minus a half, using the power law for differentiation. And since u equals x squared plus 3, du dx is therefore 2x. We then substitute back for u to obtain an answer in terms of x only. And this gives us the following upon simplifying. Here's a final example. y equals e to the power of x squared plus 1. Setting our inner function u to be x squared plus 1, y is therefore e to the power of u. In accordance with the chain rule, we differentiate y with respect to u, and u with respect to x separately, and then multiply these two smaller derivatives together. Remember to make sure your answer is in terms of x only. Alright, it's time to pause the module and have a go at differentiating the following composite functions using the chain rule. As with the above examples, the technique involves first identifying the inner function u, and then writing y in terms of u. You then work out dy du and du dx, and multiply them together in accordance with the rule. Again, remember to make sure that your answer is in terms of x only. Here are the answers to the practice questions.